In this video, we're going to go through calculating reaction rate. The essential question that we're going to answer is how can you determine how quickly reactants turn into products during a chemical reaction? So the first thing we're going to do is talk about reaction rate and reaction progress. So reaction rate measures how quickly reactants are converted into products. And we measure this usually in molarity per second. And remember, molarity is capital M. Now, as a reaction occurs, reactants are used up, so their concentrations are going to decrease, and products are formed, meaning their concentrations are going to increase. Think about when you're baking. You have your ingredients, and you have whatever it is you're baking, cookies, brownies, Rice Krispie treats. So as you use up the ingredients, you are making cookies, brownies, Rice Krispie treats. Those are the products. So same thing applies. Now, to calculate our reaction rate, or the rate that the reaction is progressing, we're going to take the change in concentration and put it over the change in time. So just like meters per second measures the rate that you are moving over time, the average rate in chemistry measures the change in concentration over the change in time. All right, so let's look at an example. So here we have the reaction A goes to B. We have a data table. So this data table shows different periods of time, and it shows the concentration or the molarity of A and B. Now, when you see something represented in brackets like it is here, that represents concentration. So you may in the future just see something written as this. So it'll be brackets and A, and that represents just concentration. So you may or may not see units. Just know that if you see it written in brackets, that means concentration. So here, it's asking us to calculate the average rate of disappearance of A from 20 seconds to 40 seconds. So let's take a look at our data table. And from 20 seconds to 40 seconds, we're looking at these two data points right here. So 20 seconds to 40 seconds. Now, specifically, we're talking about A, so we're just going to look at the first two columns. And remember, rate is calculated by the change in concentration over the change in time. So when we do this, we always want to take our second data point minus our first data point. And remember, rate is going to be our change in concentration over the change in time. So let's just go down here. So it's going to be our change, or our delta. Oops, let's try that again. So it's going to be our change in concentration, or our change in molarity, over our change in time. Okay, so our change in concentration. So we're going from 30 to 50, sorry, we're going from 54 to 30, so we're disappearing, but we're still going to subtract this. So it's going to be 0.3, which is our second data point, and we started at 0.54. And then we're going to subtract the time. So we went from 20 seconds to 40 seconds. We always use our second data point, so 40 minus 20. So if I plug this into our calculator, now we are going to get a negative number, but we always represent our rates as a positive number. So if it helps you, you're taking the absolute value of this when you calculate your rates. Okay, so this is going to be 1.2 times 10 to the negative 2. And our units are molarity over seconds. So my units will be molarity per second. That's it. All right, let's move on to another example. Same data table, same reaction. This time we're calculating the rate of appearance of B during the first 20 seconds. So the first 20 seconds would be from 0 to 20, and we're looking at B. So we're going to set this up just like the last one. So it's going to be the change in concentration over the change in time. So we always use our second data point, which is going to be, for concentration, 0.4 minus 0, that's our starting concentration, over our second time point is 20 minus 0. So when I plug this into our calculator, I get a positive number this time, 2.3 times 10 to the negative 2, and my units are going to be molarity per second. Now be careful when you're entering these into your calculator. So for the last one, when you enter these into your calculator, you want to make sure you use parentheses around the top and the bottom when you type it in. Otherwise, it will not read it as a fraction. Okay, same thing down here. This one you could have actually just dropped the 0. So I could have done 0.4 over 20. But again, when you enter it, make sure you use parentheses on your calculator so it sees it as a fraction. All right, let's take a look at something that's a little different. This time we have an actual chemical reaction, and it says, given the rate of formation of O2 is 0.0084 molarity per second, calculate the rate of disappearance of N2O5. So we know that the rate of formation of O2 is this. So O2 is here in our reaction. And it's asking us to find the rate of disappearance of N2O5, which is over here. Now, looking at our equation, going from O2 to N2O5, it's a rate of 1 to 2. So thinking about this reaction, for every 2 N2O5s that are used, we're going to produce 1 O2. Or another way to think of it is the rate of disappearance of N2O5 is going to be double the rate of appearance of O2. So let's set this up. So we're going to use stoichiometry here. We're going to do just a mole ratio. So the rate of formation is 0.0084 molarity per second of O2. And let's go ahead and set up a mole ratio. So for every 1 mole of O2, you are going to have 2 moles of N2O5. Okay, so when I plug this into my calculator, I'm just going to be doubling our rate of formation, and I will get 0.017 molarity per second. And this is going to be the rate of disappearance of N2O5. Okay, here's a similar problem. It says, given the rate of appearance of O2 is 6 times 10 to the negative 5 molarity per second, calculate the rate of disappearance of O3. So we're given the concentration, or we're given the rate of appearance of O2, and it's asking us about the rate of disappearance of O3. So we're going to set this up just like the previous example, and we're going to start with our our rate of appearance of O3, so 6.0 times 10 to the negative 5 molarity per second. This is the rate of appearance of O2. And I'm going to use a mole ratio, just like I did in the last example. So O2 is 3, so every 3 moles of O2, we are going to have 2 moles of O3. So when I plug this into my calculator, carefully, I end up with 4.0 times 10 to the negative 5 molarity per second. And this is going to be for O3. So that's the rate of appearance of O3. Sorry, the rate of disappearance of O3. Should drink more coffee when I screencast. All right, here's a doozy. Number 4 says calculate the average rate for each time interval for the reaction. So we're going to actually need to do a couple different calculations. So there are 3 different time intervals. So from 0 to 10.5, that would be number 1. And then from 10.5 to 22.3 seconds. And then finally, from 22.3 to 35.7 seconds. So we're going to need to do 3 separate calculations here. And we're going to need some more space. So let me add another page here. All right, so I'm going to bring our data table down. Just plop this in so we don't have to keep flipping back and forth. So again, we have 3 different calculations going on here. So let's start with our first interval here. So when we set this up, it's going to be just like the previous example. We are going to start with our second concentration. So 0, let's try to use the same color scheme here. So 0.0045, that's our second concentration, minus our initial, which was 0.0050. And we're going to put that over the change in time. So the second time point is 10.5. And our first time point was 0. Okay, so when I plug this into my calculator, I get 4.8 times 10 to the negative 5 molarity per second. Okay, our second time interval was this one right here. So our second concentration was 0.0040. Our first time point was 0.0045. Okay, and then the difference in our time, so our second time point was 22.3, and our first time point was 10.5. Okay, so when I subtract here, I get 4.2 times 10 to the negative 5 molarity per second. So notice our rate is going down. We'll come back and talk about why in a second. All right, and then our last set of points, we've got 0.0035, and our first point is 0.0040, and our difference in time, 35.7 minus 22.3. I plug that into my calculator, I get 3.7 times 10 to the negative 5. That's it. So notice our rate drops. So from each point here, our rate is dropping. And if you notice, the reason it's dropping is because our concentration is getting used up over time. So our reactants are being used up. So as the reaction progresses, the concentration of our reactants is less. So therefore, our reaction is going to move at a slower rate. All right. So as I just mentioned in our previous example, our reaction rate is going to decrease as the reaction continues because the concentration of the reactants decreases. So think about these 2 points in time. Let's just pretend these containers are of identical volume. So going from container 1 to container 2, as our concentration gets up or gets used up, more or fewer particles are available to collide and for a reaction to take place. Now, an instantaneous rate is the rate at a specific moment in time. This is found by calculating the slope of a tangent line to the concentration versus the time curve at any given point. So think about when you're driving an automobile, it's not calculating your average speed, it's calculating your instantaneous speed at any given point in time. So let's take a look at this example. So it says calculate the instantaneous rate, t equals 2 minutes, given the slope tangent as 0.056 molar over 2 minutes. So our instantaneous rate, we're going to find by calculating the slope of the tangent line to the concentration versus time at any given point. So we're going to find it at exactly 2 minutes. And we're told that this is the rate at that point. Sorry, it's not the rate, that's the concentration, and that is the time. So we're going to take 0.056. That's our concentration, and at 2 minutes. So we end up with 0.028 molarity per minute. So I could have gone back and calculated the instantaneous rate at any given point in time by just picking one line off of our data table here. So any of those four I could have used to calculate our instantaneous rate. But our average rate is over a given period of time, so that's why we're using 2 points here. And that's it.